Alright guys, so I'm gonna have to do a voiceover because the audio is pretty bad. So here's number 78 from the textbook here. So a solid uniform sphere, radius r is placed on the inside of a hemispherical bowl with much larger radius r, and it's released and we find the speed or the velocity or whatever I was asking at the bottom. Alright, so here we have our little half bowl because we only care about from where it starts to where it gets to the bottom. And then the radius of the little ball is little r, and then the radius of the actual bowl is big R. And then we label where it starts, the height, h, right? Like that. And so starting off, we have a spherical ball, I think it's gonna go right now. And it's gonna be a sphere, and because it's rolling without slipping, right, we need to do inertia, right? So inertia of a sphere is 2/5 mr, little r in this case, because that's the radius of the ball, mr squared. And then we can basically get started with the rest of the problem, and that's just gonna be transferring of energy, right? Because slipping, it's not slipping, right? So first of all, it starts with potential energy mgh, and then that transfers to mechanical energy, rotational mechanical energy, and actual translational mechanical energy. So that's 1/2 I omega squared, which is the rate of rotation squared, times 1/2 mv squared, which is the speed at the bottom, right? And then we just simplify. We take our I, and then we plug it in, and then omega here. So think of the track and a ball rolling on the track, right, with radius r, with a speed v, right? And so it's turning at a rate omega, right? Just think of the track, right, the same way. And so basically it's turning at a speed of omega, and with the radius r, you just multiply the r times omega and you get velocity. And you can do the simple math behind it. It's pretty easy to derive why it happens, but then we basically just get our translation, which is omega is equal to v over r, and then we just plug that in for omega, so that becomes omega squared becomes v squared over r squared, and then plus 1/2 mv squared. Cancel out all the m's, and then you get gh is equal to 1/2 plus 1/5 is going to be 5/10 plus 2/10, 7/10 r squared, or v squared, my bad. There you go, yeah. And you can barely tell that's a v, but that is a v. And then your velocity is equal to 10/7, kind of cut off there, sorry, gh. And is that what the problem asks for? No, the problem asks for its rotational speed, angular speed at the bottom, right? So it's just a little bit more work. Could have solved directly for rotation, but oh well. We'll just finish it off right here. Just a second to erase everything, because my little whiteboard's not that big. Alright, so then v is equal to 10/7 root gh all over square root, all under square root, right? And we want omega at the bottom, right? And that omega, as we already know, it's all equal to v over r. And we also need to simplify h, because we want to do it in terms of the angle that the ball starts, right? And that angle, it was defined in the problem, it's as theta, right? Big R is the radius of the big ball. Theta inside is the angle at which the sphere starts. And so h is then going to be r minus r cosine theta. And simplify a little bit, r 1 minus cosine theta. There you go. And you just plug everything in, plug and chug, basically. So we get as a final root 10/7 g r 1 minus cosine theta over little r is gonna be our angular momentum. And that is it, folks. That is the problem. It's really not that bad when you just go ahead and start it. Alright, bye bye.